Every single time you send an email or buy something online or even just browse the web, there's this hidden battle being waged. It's a high-stakes, totally invisible arms race between the people who create secret codes and the people who break them. Today, we're going to dive into that story, the story of modern cryptography.
I mean, this is the fundamental question, right? It's a problem people have wrestled with for literally thousands of years. How can you send a message that only one other person can read, especially when you know that message has to travel through public, insecure channels where pretty much anyone could be listening in?
So how do you solve that? Well, the first and, the most intuitive solution is one we've been using for centuries, and it's called the classic secret key.
The idea is super simple, really. Let's imagine our two classic characters, Alice and Bob. Before they need to send any secrets at all, they just meet up and agree on a single shared secret key. You can think of it just like a physical key that can both lock and unlock the very same box.
And the process itself is incredibly straightforward. Alice takes her message, what we call plain text, and uses that key to scramble it into something called ciphertext. Now, this ciphertext is just complete gibberish to anyone who doesn't have the key. She sends it over to Bob, and he uses that exact same key to unscramble it right back into the original message. Simple, effective, and perfectly secure, with one huge catch. No one else can ever get their hands on that key.
But that's where we hit a massive problem. This classic method has a fundamental flaw, one that makes it almost useless for our modern world. And this is what's known as the key exchange dilemma.
So, if the method works so well, what's the big deal, right? What's the catch that forced us to invent something totally new?
And here it is, in a nutshell. If Alice and Bob are in the same room, no problem. They can just whisper the key to each other. But what about the internet? What if Alice is in Tokyo and Bob is in Buenos Aires? How do they agree on a key then? If she sends it in an email, an eavesdropper can just snatch it, and now every single secret message they send is wide open. This is the key exchange dilemma, and for a long time, it was a huge roadblock. So, to solve this, cryptographers back in the 1970s came up with one of the most revolutionary ideas in all of computer science, an idea that would change absolutely everything. It's called public key cryptography. Now, this is a complete paradigm shift. Instead of one shared key, every single person gets a pair of keys that are mathematically linked together. One is your public key, and you can shout this one from the rooftops, post it on your website, email it to everybody. It's public. The other is your private key, and you guard that thing with your life. You never, ever share it. And this is how it completely sidesteps that whole key exchange problem. Now, anyone can find Bob's public key and use it to lock a message for him. But here's the magic. Only Bob's private key can unlock it. Alice never has to send a secret key to anyone. She just grabs his public key, locks her message, and sends it off, completely confident that only Bob can ever read it. The dilemma is just gone. This new method, especially the famous RSA crypto system, was seen as this monumental breakthrough. Back in 1977, the legendary writer Martin Gardner introduced RSA to the world with this incredibly confident headline. He even published a challenge message encrypted with it, basically daring anyone on Earth to try and break it.
Millions of years. Wow, that's quite a prediction. But this is an arms race, remember? So the obvious question is, how well did that prediction actually hold up?
Not millions. 17. In April of 1994, the code was cracked. But the truly amazing part isn't that it was broken, it's why it was broken so much faster than anyone could have possibly imagined. So basically, three things happened that the 1977 prediction just couldn't fully account for. First, raw computing power just exploded. Second, mathematicians discovered way smarter, more efficient algorithms for factoring large numbers, which is the hard math problem RSA relies on. And third, a total game changer happened, the internet. All of a sudden, thousands of computers all over the world could work together on the same problem, a massive distributed effort that was just unthinkable back in '77. And this really gets to the heart of the entire story. Computational security, security that's based on a math problem being too hard to solve, is always a moving target. It's not some permanent guarantee of safety. It's just a temporary lead in the race between the people building the locks and the people building ever better lockpicks. And just as we've built our entire modern digital world on these public key systems, a new kind of lockpick is starting to appear on the horizon. And this one is so powerful, it threatens to shatter everything we've built. And no, that's not an exaggeration. The threat comes from a completely new type of machine, a quantum computer.
It works on principles that are so different from today's computers that it could make those hard math problems our security relies on, well, suddenly very easy. Look, a practical, large-scale quantum computer would be a catastrophe for our current public key infrastructure. The mathematical foundations of systems like RSA, the very things that make them secure today, would just crumble. It would be like a master key for a huge portion of the internet's secrets.
But hey, remember, this is an arms race, and the code makers are not standing still. They are already hard at work building the next generation of defenses for what we call a post-quantum world.
So you can see the cycle here, playing out again and again. For every problem, a brilliant solution is found. But that solution always seems to create a new, even more complex problem. First, the key exchange problem led to public key crypto. Now the quantum threat to public key crypto is leading us to the next phase, a field called post-quantum cryptography. The goal here is to build new systems based on math problems that even a quantum computer would find impossible to solve.
It really leaves you wondering, doesn't it? As technology accelerates, this race between secrecy and discovery only gets faster and faster. It makes you question if unbreakable is even a real thing, or if the best we can ever hope for is to just stay one single step ahead in this unending arms race. Thanks for joining me for this explainer.